Okay, let's dive into this. Welcome to today's Explainer, where we're unpacking one of the absolutely most exciting concepts in physical science, acceleration and changes in motion. Every time you move, you're basically a highly tuned sensor experiencing the laws of physics in real time. So let's look closely at the science behind how and exactly why things change how fast they're moving. Right off the bat, I want you to imagine you're standing at the very top of a ramp on a skateboard. You lean forward and you drop in. What exactly is happening to your motion in that very split second? You don't just magically transport to the bottom at one constant speed, right? No way. You start from a complete standstill, and as you travel down the ramp, you go faster and faster and faster. You can literally feel the wind hitting your face a little harder with every passing second. That thrilling, stomach-dropping feeling, that's the real-world sensation of your motion actively changing. That is physics in action. So to make sure we get the absolute most out of our time today, let's quickly hit our learning target. By the end of this explainer, you're going to be able to easily distinguish acceleration from constant velocity, you'll interpret a change in velocity over time, and use a data table or a graph as concrete evidence. Okay, to understand acceleration, we first have to lock down a few basic definitions, starting with velocity. Velocity is simply the speed of an object in a specific direction. Now, it's really important not to confuse this with just speed. Look at it this way. If you tell me you're running at 5 meters per second, you've just given me your speed. But if you tell me you're running 5 meters per second north, well, now you've given me your velocity. It's the whole package. It's both how fast you're going and exactly where you're headed. Next up, we have time. In physics, time is the interval over which motion occurs. We need a reliable way to track when these movements and shifts actually happen. Think about it. If you change how fast you're going, it doesn't just happen in 0 seconds, right? It takes a certain amount of time for that shift to take place. Time is kind of like the invisible track that all of our motion runs on.
Now we bring those pieces together to look at change in velocity. This is just the difference between an object's final velocity and its initial or starting velocity. When we talk about a change, it means you aren't just coasting along on cruise control. Something fundamental about your motion is actively shifting. You're either speeding up, slowing down, or turning. If your starting speed and your ending speed are different, boom, you have a change in velocity. Which brings us to the absolute star of our show, acceleration. Acceleration is defined as the rate at which velocity changes over time. Whenever you hear the word acceleration, I want you to immediately think of the word change. If your velocity is changing over a certain amount of time, you are accelerating. It's the core concept that links our previous definitions of velocity and time together into one really powerful, dynamic package. Now, what's really interesting about this slide is this phrase, rate of change. In science and math, rate of change describes exactly how quickly one variable changes relative to another variable. In our case, we're looking at how quickly your velocity changes relative to time passing by. It's not just the fact that you sped up, it's how fast you sped up. Did you go from 0 to 60 in 3 seconds, or did it take you an entire hour? The rate of change gives us the exact mathematical measurement of that motion. When we want to look at this rate of change visually, we use slope. Slope is the steepness of a line on a graph. If you were to plot your velocity over time on a graph, the steepness of that line would act as perfect visual evidence to show us exactly how fast your acceleration is happening. A super steep hill on the graph, that means a massive, sudden acceleration. A gentle flat hill, that means a very slow, gradual change. Before we look at some actual numbers, we really need to clarify our units. Velocity is measured in meters per second, written as m/s. But acceleration is measured in meters per second squared, written as m/s squared. Why squared? Well, because you're taking a velocity, which is already meters per second, and dividing it by time again, so it's meters per second per second. It kind of sounds like a tongue twister, I know, but using these specific units ensures you can confidently label your calculations and communicate your findings like a total pro. Okay, let's look at a beautifully simple data table. On the left, we've got our time in seconds, ticking up 0, 1, 2, 3. On the right, we have our velocity in meters per second. Notice what's happening as we read down the table. At 0 seconds, the velocity is 0. We're at a total standstill. At 1 second, velocity is 2. At 2 seconds, velocity is 4. At 3 seconds, it's 6. The velocity is steadily increasing by exactly the same amount, 2 meters per second every single second. So the crucial point is knowing how to pull the acceleration out of that data, and we do that by calculating the rate of change. Let's just follow the steps. Step 1, pick any 2 points from our table. Let's use the points at 1 second and 2 seconds. Step 2, find the change in velocity. At 2 seconds, we were at 4 meters per second, and at 1 second, we were at 2 meters per second. 4 minus 2 equals a change of 2 meters per second. Step 3, find the change in time. 2 seconds minus 1 second is 1 second. Finally, step 4, divide them. 2 divided by 1 gives us a rate of change or acceleration of 2 meters per second squared. See, you just mathematically proved the acceleration. Now that we've done the math, let's contrast the two main states of motion you really need to know. On the left, we have constant velocity. This is that effortless feeling of cruising at a steady speed in a completely straight line. Your cruise control is on, the road is totally flat, and you aren't turning the steering wheel at all. On the right, we have acceleration. This is dynamic. You're hitting the gas to speed up, hitting the brakes to slow down, or turning the wheel to change direction. Constant means zero change, acceleration means active change. Pay very close attention to this next concept, because honestly, this is where a lot of people get tripped up. In physics, we use signs to indicate direction. A positive sign usually means you're speeding up in a positive direction, like moving forward. A negative sign usually means you're slowing down or moving backward. And here is a massive misconception alert. The word deceleration is not a separate scientific category. In physics, slowing down is firmly classified as acceleration. It's simply acceleration in the direction opposite to your motion. So whether you mash the gas or slam the brakes, from a physics standpoint, you are accelerating. Absolutely mind-blowing, right? All right, let's put your new knowledge to the test. Listen to this scenario, briefly pause the video, and think of the answer. If a car is moving at a steady 50 meters per second in a completely straight line, what is its acceleration? Take a quick moment. Got it? The answer is 0 meters per second squared. If you got that right, fantastic job. But why is it 0? Remember our definitions. The car is moving at a steady speed in a straight line. The velocity is not changing. And if there is no change in velocity, there is absolutely 0 acceleration, no matter how ridiculously fast that car happens to be moving. Let's try one more quick math challenge based directly on the steps we just covered. A skateboarder goes from an initial velocity of 2 meters per second to a final velocity of 6 meters per second. This change happens over exactly 2 seconds. What is their acceleration? Pause for a second and try the mental math. And this brilliantly illustrates the formula in action. The answer is 2 meters per second squared. Let's walk through the reasoning real quick. The change in velocity is the final minus the initial, so 6 minus 2 gives us a change of 4 meters per second. We divide that change by the time it took, which was 2 seconds. 4 divided by 2 equals a rate of change of 2 meters per second squared. Excellent effort. All right, let's lock in everything we've built today. Constant velocity means 0 change, while acceleration is a calculated change in velocity over time. We can confidently use the slope on a graph, or the rate of change from a data table, as hard mathematical evidence of this motion. And above all, remember that hitting the brakes and slowing down is still a form of acceleration. I'm going to leave you with a provocative transfer question to keep your scientific brains working long after we're done here. If you toss a ball straight up into the air, what happens to its velocity and its acceleration at the very top of its path? Think about that split-second moment where it completely stops before falling back down. Is it accelerating? What's its velocity right then? Take everything we explored today and apply it to that falling ball. Thanks so much for joining me on this explainer, and keep questioning the world around you.